Hypothalamus artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for Pandemic Management Decision Support System. Part 4. Epidemic Economic Impact Model. Conference prepared and edited by Jesus Velasquez Bermudez. His resume can be found on LinkedIn. The presentation consists of 5 videos, and their supporting documents, which summarize all the applied research work carried out by HI, to contribute its knowledge in highly complex mathematical modeling, to the optimized management of pandemics such as COVID-19. These are: Pandemic Management using Advanced Artificial Intelligence, Epidemic Simulation Model, General Epidemic Optimization Model, Epidemic Economic Impact Model, and Kalman Filter Estimation Model of the Epidemic State. The models corresponding to Part 4 and 5 are designed, but have not been implemented. Users of these mathematical models can be grouped into information technology companies, government, universities and research centers, and private enterprises and gremial organizations. The result of the research and mathematical models carried out by Hypothalamus Artificial Intelligence, it is considered a public good, because it is of benefit to all humanity. Therefore, HI is willing to offer them at no cost to nonprofit organizations, mainly in developing countries. HI is also interested in being part of research groups working on pandemic management. Pandemics Management. Epidemic and Socio-Economy Model. As Albert Einstein put it, to raise new questions, new possibilities, to regard old problems from a new angle, requires creative imagination and marks real advance in science. A new paradigm for epidemic management. The management of a pandemic based on traditional control policies, mainly on epidemiological criteria, without considering the future socio-economic impact, does not seem to be indicated in the era of Industry 4.0. Which stands out for the great ability to project the future, to make the best decisions, using the computing power derived from computational technologies, and the exponential advance of the ability to model high complex systems. Therefore, it is required a different paradigm for the modern epidemic management. The main economic impacts to be assessed with respect to the consequences of epidemic control policies in the economy are bankruptcy of enterprises, unemployment people, migration between social classes, productive chains, mobility between regions, and quality of life indexes. Given the strong impact of epidemics at the regional level, modeling should be geared towards shaping the regional economy and not shaping the country's economy, and then disaggregated at the region level. The socioeconomic model is aimed at determining the socioeconomic impact of epidemic management at level of each region of a macro region. Balancing decision-making between two contradictory objectives, minimizing in the short term the number of deaths in the short term and conjunctural, and maximizing in the long term the population's quality of life indices, structural. It is a multi-criteria optimization model. Ignoring in the management of the pandemic in the short term, the long-term socioeconomics effects, is the most serious mistake that can be made. While it seems that the ethical thing to do is to defend a short-term life, it is also true that it is ethically wrong to condemn millions of lives to poverty and hunger in the future. This duality is not easy to solve. Anticipation. It is the core of decision-making under Environment 4.0. It is not a question of reconstructing the damage caused by a disaster, with decisions a posteriori. It is about anticipating and mitigating with actions before the disaster. And the best way to do that is to use the mathematical modeling power under the new technological paradigm. Stable, unstable and chaotic dynamic systems. The pandemic is an event that changes the behavior of a stable socioeconomic system. Basically, dynamic systems can be classified into stable, unstable, and chaotic. Chaotic and/or unstable behavior exists in many natural systems, including fluid flow, heartbeat irregularities, weather and climate. It also occurs spontaneously in some non-natural systems with artificial components, such as the economics, stock markets and road traffic. Chaos theory has applications in a variety of disciplines, including meteorology, anthropology, sociology, physics, environmental science, computer science, engineering, economics, biology, ecology, and philosophy. One of the main features of both unstable and chaotic systems is that they have a high dependence on the initial conditions. This differentiates them of stable systems. From a stable system from which its characteristic temporal evolution equations are known, and with fixed initial conditions, it is possible to know exactly its evolution over time. This means that despite perturbations in the initial conditions, it always converges to the same point, or to a very close one. But in the case of unstable and chaotic systems, a slight difference in the initial conditions causes the system evolves completely differently. The theory formed the basis for such fields of study as complex dynamical systems, edge of chaos theory, and self-assembly processes. A system is stable when two solutions with sufficiently close initial conditions remain close over time. Thus, a stable system tends over time to a point of attraction, or orbit. In the case of economics, they can be studied with models of general computable equilibrium. This is not the situation of the economics during/after the pandemic period. The economy will lose stability and take a long time to recover. Therefore, the economic models used to describe a stable economy are not useful for describing the dynamics of the economy during the pandemic. A system is unstable when two solutions with different initial conditions end up diverging as small as the initial conditions. Thus, an unstable system escapes the attractors, and it can be very difficult to determine what will happen over time. This may be the situation of the economics during and after the pandemic period. Without tight control of the economy, it can go to any point. A system is chaotic when two dynamic solutions are kept at a finite distance close to a point of attraction. The solutions move irregularly, and after time both solutions are not close. That way, the system remains oscillating in an area of its state space, but without tending to a fixed point of attraction. This may be the situation of the economics during and after the pandemic period. For real systems, this unstable, or chaotic, behavior can be studied through the built and the analysis of a mathematical model that explain the system behavior, studying and integrating the known dynamic behavior of each of its components, trough a bottom-up model of the system. The decision-making during the pandemic process aims to make the best decision for society, which is not easy, nor intuitive. The problem is further complicated when decisions must be made with real constraints on available resources, and when it must consider the socio-economic impact derived from the pandemic and its control. The traditional goal of pandemic management focuses on modifying the natural behavior of the pandemic, solid curve, through sanitary controls, in order to reduce the peak of infected people, striped curve, and thus save lives by reducing the deficit of hospital resource capacity. However, it should be noted that the two curves have the same integral, and in theory when time tends to infinity, the amount of the infected population will be equal. If hospital resources are sufficient, there is no reason to delay the peak, and as the pandemic spreads, the negative socio-economic impact will be greater. The traditional tool is to use simple epidemic simulation models, trying to predict the future of the pandemic, before different control measures, and thus select, based on perception, which is the best decision. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. In the case of the epidemic, Hai has conceptualized the epidemic management hypothalamus based on 4 models: epidemic model, logistic model, economic model, and control and surveillance model. This video is related with the epidemic economic impact model. Epidemic modeling. The SEIMR/RS general epidemic model it is considered suitable for the proposed modeling. For those interested in knowing more about this model are invited to watch the video. SEIMR/RS Epidemic Simulation Model. SEIMR-RS corresponds to a generalized mathematical model of pandemics that enhances traditional, aggregated simulation models when considering interregional impacts in a macro region. SEIMR-RS also considers the impact of modeling the population divided into socio-demographic segments based on age and economic stratum, it is possible to include other dimensions, for example, ethnics, gender, etc. SEIMR-RS is the core of the SEIMR-RS OPT Epidemic Management Optimization Model, that determines optimal policies, for example, mitigation and confinement, considering the spatial distribution of the population, segmented socio-demographically. SEIMR-RS can be understood and used by any epidemiologist, and/or physician, working with SEIMR or similar simulation models, and by professionals working on the issue of public policies for epidemic control. SEIMR-RS was carried out in a Java program. This program may be used by the organizations that considers the SEIMR-RS will be useful for management the COVID-19 pandemic. Economic modeling. The proposed model is based on incorporating in a single model, the modality of the pandemic, the optimization of the resources required to face the pandemic, and build the economic model considering all the necessary theoretical aspects, in order to quantitatively estimate the socio-economic impacts of the pandemic control policies. With this information, public health authorities will be able to know precisely the consequence of their decisions. The current modeling capacity, unit to the computational power, allows to manage the pandemic with mathematical models of high complexity. Although the problem is originally biological, its modern management is a problem of mathematics and intensive use of artificial intelligence. Economic equilibrium. City-region. Cities correspond to a region within a region, or a country, and therefore the study and modeling of their economy must be analyzed considering this inevitable peculiarity. Therefore, the general concepts of the economy of a country are simply the starting point for the modeling of the region, but they must be adjusted to consider the economic relations that derive from its regional character, which implies relations with other regions, and especially with those with which it has a strong physical interconnection that allows free flow of products, people, and many other production factors. Therefore, interregional economic relations are fundamental in the process of spreading the pandemic. HI has implemented a model to describe regional equilibrium, based on the paper migration, unemployment and development. A two-sector analysis, which can be described as an economic model, with unemployment, for two neighboring regions, urban and rural, characterized by production and income. A fundamental argument of Harris and Todaro is that in many developing countries, the existence of an institutionalized urban minimum wage, at levels substantially higher than those allowed by the free market, leads to an equilibrium with considerable urban unemployment, coupled with a migration process that is a phenomenon of disequilibrium. This aspect is of fundamental importance in the socio-economic consequences of the pandemic. Not all pandemic sanitary control policies will bring the same consequences, therefore they cannot be ignored by decision makers. The HI multi-regional economic model was applied to a case with 1 city, 2 productive sectors, S1 and S2, and 2 regions, R1 and R2. For simplicity of analysis, it is considered that the industrial sector is on the city, and that in the rural regions, there is only agricultural production. The problem focuses on finding the amount of labor hired in each productive sector, and the corresponding remuneration. The table presents the results obtained for the hypothetical case. Regional modeling must integrate the country, or macro-region, and the different regions. There are 2 basic approaches to face the problem. Top-down model. In this case, the national economy is modeled, and then the behavior of the regional economy is disaggregated, based on empiric rules. Bottom-up model. In this case, a regional economic model is used. It makes possible to assess the equilibrium between regions, and the interregional transfers of factors of production, as well the remuneration of these factors. Modeling may involve constraints that the national economy must satisfy, for example the totality of the production factors at the country level. Additionally, the border conditions with the external sector must be considered. Cobb-Douglas production function. In the production of any good or service, firms use factors of production, for example, workers, capital, such as machinery, technology, information, and other productive resources. To study the microeconomic behavior of companies, it is necessary to know how these companies are, so that the planner can determine what happens with the economy when these resources are scarce. This is the situation during and after the pandemic. In economics, The Cobb-Douglas function is a form of production function, Q, widely used to represent the relationships between a product and variations in inputs technology, T, labor, L, and capital, K, to estimate a country's production function and thus project its expected economic growth. It was proposed by Knut Wicksell, 1851 to 1926, and investigated with respect to concrete statistical evidence, by Charles Cobb and Paul Douglas in 1928, also applies industrial economic sectors and/or large industries. Cobb-Douglas production function. In the production of any good or service, firms use factors of production, for example, workers, capital, such as machinery, technology, information, and other productive resources. The general structure of Cobb-Douglas, including in technology, is presented in the image. The above equation is mathematically complex, with an exponential structure, that must be modeled directly or using logarithms, which complicates the solution of optimization problems. Therefore, it is suggested to perform modeling based on a convex hull of the Cobb-Douglas function. An example of a curve, it is used to present the concept bidimensional associated with a grid L, K, a convex hull, that summarizes the production for each pair L, K. Interregional input-output Leontief model. Vasily Vasilyevich Leontief was a Soviet-American economist known for his research on input-output analysis and how changes in one economic sector may affect other sectors. Leontief won the Nobel Memorial Prize in Economic Sciences in 1973, and 4 of his doctoral students have also been awarded the prize. In economics, an input-output model is a quantitative economic model that represents the interdependencies between different sectors of a national economy, or different regional economies. While national input-output tables are commonly created by country statistics agencies, officially published regional input-output tables are rare. Therefore, economists often use location quotients to create regional multipliers starting from national data. This technique has been criticized because there are several location quotient regionalization techniques. Transportation is implicit in the notion of inter-industry flows. It is explicitly recognized when transportation is identified as an industry. But this is not very satisfactory because transportation requirements differ, depending on industry locations, and capacity constraints on regional production. Also, the receiver of goods generally pays freight cost, and often transportation data are lost, because transportation costs are treated as part of the cost of the goods. The image shows a full Leontief matrix that divides outputs into intermediate use and final demands. To model regional economics to see the spatial economy and transportation implications of input-output analysis, SEIMR developed the concept of interregional input-output. To know the interregional commodity flows, an export column is introduced into the table, and an import row. A more satisfactory way to proceed would be to tie regions together at the industry level. That is, we could identify both intra-region, inter-industry transactions, and inter-region inter-industry transactions. The problem here is that the table grows quickly. Today, it is not a computer problem, it is a data problem. Input-output is conceptually simple. Its extension to a model of equilibrium in the national economy has been done successfully using high-quality data. One who wishes to do work with input-output systems must deal skillfully with industry classification, data estimation, and inverting very large, ill-conditioned matrices. Moreover, changes in relative prices are not readily handled by this modeling approach alone. Input-output accounts are part and parcel to a more flexible form of modeling, computable general equilibrium model. Unfortunately, because of the pandemic, the use of this type of model is questionable. 2 additional difficulties are of interest in transportation work. There is the question of substituting one input for another, and there is the question about the stability of coefficients as production increases or decreases. These are intertwined questions. They have to do with the nature of regional production functions. The table presents an academic example of a Leontief matrix. In this case, the sectoral demand are, Sector 1, 400 units, Sector 2, 4,650 unit. To meet these demands, Sector 1 must produce 2,500 units, since 500 are consumed, as an intermediate product, in Sector 1, and 1,600 in Sector 2. In turn, Sector 2 must produce 8,000 units, of which 1,750 are consumed in Sector 1, and 1,600 in Sector 2. On the other hand, 5,050 units of labor are required, 250 for Sector 1 and 4,800 for Sector 2. In addition to labor, production requires basic inputs such as transportation, energy, water, etc. Lenschieff's matrix corresponds to a restriction of industrial production. What cannot be produced in one region must be imported from other regions, and surpluses must be exported. If inventories are considered, one can have a more realistic dynamic Leontief model. In an epidemic, one of the control measures is the confinement and closure of certain industrial sectors. The confinement will lead to a decrease in the availability of labor, which will decrease industrial production. The closure of public transport will bring similar consequences. The closure and reopening of industrial sectors should consider the Leontief model, since doing so in an intuitive manner may have null or counterproductive effects. For example, if airlines and hotels have been closed, the isolated reopening of hotels does not imply their reactivation, since much of their demand requires airlines. Spatial economics and people mobility. HI has developed high RPO, a model oriented to explain the growth of a conurbated region, based on land use policies, and the distribution of people, companies, facilities, and the multimodal transport system in the region. To determine mobility during and after the epidemic, high RPO may be used, which simulates and detail the mobility processes in the space characterized by I. Modes of transport, 2. Hours of traffic, 3. Transport network, 4. Location worker housing, and v. Location of companies. High RPO include a georeferenced model that it divides the space into basic territorial units, BTU or zones, and uses a multimodal transport network for the movement of people and the transport of goods. Each BTU is characterized socioeconomically by the parameters that define the economy that is given in the BTU: housing, equipment, people, companies that occupy the space. To determine people's mobility, MC. Fadden's theory of random utility theory is used. The data model and definition of algebraic elements of high RPO are assumed as an integral, complementary, part of the high health model. The relations between the epidemic and socio-economy model are established considering movement restrictions on people imposing control policies, and restrictions on productive capacity imposed by control policies. More detailed information about high RPO can be seen in another video. Integrated regional planning incorporating economy, logistics, infrastructure, and land use. The fundamental theory of high PRO is presented in a mathematical programming model for regional planning incorporating economics, logistics, infrastructure and land use. And in the paper, a decision support system for regional planning of large regions using mathematical programming. High RPO integrates four major systems operating in the region: inhabitants, enterprises, facilities, and land use. These systems are connected trough the transport and logistics system, and use the energy systems. These subsystems are integrated by multiple networks, the most important of all, the multimodal transport system. High RPO is composed of 8 models that together project the development of the region in the future: inhabitants and housing, facilities, transport, and traffic, energy contamination, lands, and economic benefits, and land use. High health integrates with high HRPO. This implies that all models of the two systems can be integrated through the database, via a common data model, and by means of equations that integrate a unique holistic model, this following the principles of structured mathematical modeling. This integration is since the management of public health problem corresponds to regional planning problem, as experienced during the COVID-19 pandemic. Modeling epidemic and economics process. The hypothalamus of a pandemic decision support system can be conceived as the integration by layers of 4 models: epidemic, simulate the pandemic process; control policy, optimizes control policies; logistics, optimizes the use of health system resources; and socioeconomics, simulates socioeconomic impact. The socioeconomic model must take as input the situation of the economy at the beginning of the pandemic, and produce the impacts of the pandemic on the socioeconomic system. The model can be used from 2 points of view. Taking as input a pre-established control policy, or to produce an optimal control policy, autonomously defined by the model. The modeling implies integrating the epidemic process with the modeling of the economic process. The main economic impacts to be assessed with respect to the consequences of epidemic control policies in the economy are bankruptcy of enterprises, unemployment people, migration between social classes, productive chains, mobility between regions, and quality of life indexes. Given the strong impact of epidemics at the regional level, modeling should be geared towards shaping the regional economy and not shaping the country's economy, and then disaggregated at the region level. The link between the epidemic control model and the socio-economic model is through declining demand and the express prohibition of certain industrial activities. The basic modeling principle assumes that control policies imposed directly or indirectly limits on demand for goods and services from the industrial sectors and production capacity for reasons of industry bans. Without considering existing inventories in a sector, the production must be limited by demand and production capacity. To simulate the spatial economic and the mobility of the people, it uses the high RPO principles. To determine the impacts on regions and productive sectors, it is necessary to select those that lead the region's economy. On the other hand, production functions are required to explain the productivity of the region. Mainly, to determine the impact of the reduction of the mobility of people to go to the factories. Including the existing relationships between industrial sectors, in the different regions, is required to determine the impact derived in decrease of the production of intermediate products, that will affect the productive capacity of all sectors, and not only those that are directly affected by health control policies. The same happens with the decline in international trade, which will end up affecting regional economies. Together, all the theoretical concepts that build an economy, the central part of the model focuses on explaining how industries will evolve in the different sectors of the economy. The fundamental problem, during and after the pandemic, is to determine the economic situation of companies. In a stable state, companies will evolve, grow or decrease, for market reasons. During the pandemic, companies will decline due to the pandemic, with the possibility of bankruptcy due to lack of liquidity. Normally, they will have to exhaust their bank credit quotas to try to pass that crisis. After the pandemic, the possibilities of growth will return, but this will depend on the new situation of the company, which can be seen by a level of indebtedness that may not be able to overcome. Describing this process is the goal of the epidemic and economics model. To do this, the modeling is based on the following principles. Production is established based on an individualized Cobb-Douglas function for each economic sector in each region. The financial statement of the company is determined from the cash flow of each sector, based on an equation of income and egress, that posts sales as a function of production, and expenses based on production costs. For this, costs are allocated to each factor of production and a markup is assumed to determine sales prices considering the production costs. The company's liquidity equation determines the situation of the sector, which indicates in whether the sector is active or not. This depends on a minimum level of liquidity that can support by the economic sector. If the liquidity level of the sector falls below a certain level of liquidity, the sector close operations. The table shows some of the parameters and variables of the model. The image shows some of the equations that are used to describe this unstable economic process. In order to determine the production of economic sectors, demand satisfaction and terms of trade with other regions are considered. The general modeling hypotheses are: demand for goods and services from an economic sector can be met with domestic production or exports. Unserved demand implies a social cost, that is, demand equals domestic production plus imports plus deficit. The production of goods and services from an economic sector can be used to meet domestic demand or for exports outside the macro region, that is, production equals domestic production plus exports. Exports outside the macro region should be limited by a maximum quantity, or an exchange price could also be handled in the model to determine the exports that balance prices. The first case implies exports less than limit exports. Employment modeling is essential as it determines the income of the population, that in turn determines social mobility between different social classes. The hypotheses made for modeling are: segmentation of the workforce in each sector, payroll, contractors and informal. Displacement from different work segments should be simulated. The migration rule is that when the amount of labor used by a sector decreases, the offset is given in the following rules. Payroll moves to contractor, that moves to informal, that moves to unemployed. In addition, the labor must be differentiated by the site where it can perform its work, I, at home, 2, at home or on site, and 3, on site. This classification should be used to establish the amount of labor that can be used considering control policies. It is also required to simulate the recovery of the economy, which can be effected in the participation of the factors of the Cobb-Douglas function, since the future can lead migration from intensive labor enterprises to intensive technology enterprises. The economic indexes should be calculated to facilitate understanding the effects that are generated in the evaluation of each scenario of control policies, taking one as a reference and calculating relative variations of the same. Delta GIP, variation of the GIP for each sector for each mitigation measure scenario with respect to reference scenario. Delta UP, variation unemployment rate. If the rate increases drastically if an economy enters recession. Delta UMP, variation in informal employment. Regional Human Poverty Index, RHPI. The RHPI is a composite measure of poverty that has the following dimensions: a long and healthy life, knowledge, a decent standard of living, and social exclusion. These dimensions are believed to be non-compensatory in nature, which implies that an improvement in one dimension cannot fully compensate for equal the deterioration in another dimension. RHPI must be a result of the epidemic and economic model. Hypothalamus artificial intelligence. Invites to join to the LinkedIn group. Mathematical modeling for coronavirus pandemic. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.